Hi everyone and welcome to the channel. Today's video is the second of two videos about the ideal gas law. In the first video, we had an overview of the principles within the ideal gas law and the resulting ideal gas equation. We also applied the ideal gas equation to some practice questions involving the two most common unit combinations. In today's video, we're going to be modifying the ideal gas equation to examine other variables not included in the original equation, including density, mass, and amount in molecules. We're also going to be looking at the conditions in which the ideal gas equation cannot be applied and how a gas that is too real could be addressed with a different equation, the van der Waals equation. Okay, so in the previous video, we went through the conventional ideal gas law and the ideal gas equation. For this video, we're going to just go through the equation again quickly as a reminder before we then delve into how we can modify it for other variables that relate to the behavior of gases but are not included in the original equation. Okay, so the original ideal gas equation states that pressure multiplied by volume, which is the volume of the system, is equal to the amount in moles of the gas present multiplied by the ideal gas constant and the temperature of the system. Now, this is the first of the two most common unit combinations that are used in chemistry courses and physics courses for the ideal gas equation. In this unit combination, pressure is expressed in pascals, volume in cubic meters, amount is in moles, and temperature is in Kelvin. The ideal gas constant, which can also be referred to as the universal gas constant, the molar gas constant, or simply the gas constant, is in joules per mole per Kelvin. Joules represents pressure in pascals and volume in cubic meters because 1 pascal of pressure applied over an area of 1 cubic meter is equivalent to a force at a magnitude of 1 Newton per square meter, also being applied over an area of 1 cubic meter. This is simply referred to as 1 Newton meter, which is equivalent to 1 joule. That's the detailed technical reason, but all we must remember is that the joules in the gas constant for this unit combination represents the units of pascals for pressure and cubic meters of volume, and that the value for the ideal gas constant in this unit combination is 8.31 joules per mole per Kelvin. Okay, this is the second unit combination we most commonly see for the ideal gas equation. Pressure is in atmospheres, volume is in litres, amount is in moles, and temperature is in Kelvin. Now, the ideal gas constant, which contains the units of atmospheres and litres, moles, and Kelvin, those units are arranged as a fraction. Now, the reason why that is because this is the combination that is likely to be used for specifications that require us to cancel out units we don't want for our final answer and only use the unit we need for the variable of interest. And the numerical value for the ideal gas constant is 0.0821, and then we have our units within that fraction: atmospheres, litres, moles, and Kelvin. Okay, let's now look at how we can modify this equation to examine other variables. Okay, let's start with density. Density is the mass of a substance per volume. It could also be defined as the ratio of the mass of a substance to the volume it occupies. Basically, it indicates how much of a gas is packed into a certain volume of a system, such as a cylinder. When we usually calculate density, we take the mass of a substance and we divide it by the volume it occupies. So if we want to express density in kilograms per cubic meter, we take the mass in kilograms and we divide it by the volume in cubic meters. However, we don't tend to use kilograms per cubic meter to express the density of a gas. We tend to use that for solids. So for expressing the density of a gas, we can use grams per cubic meter. So we take mass in grams and divide it by volume in cubic meters, or we can express it in grams per decimeters cubed. So mass in grams divided by volume in decimeters cubed, or we can express it in grams per litre, which is mass in grams divided by the volume in litres. We can express these equations with symbols, so we can use the Greek letter of rho, which looks like a P. We use that to represent density, equals mass, which represents by the letter M, divided by V, which is volume, or we can use a capital D for density or lowercase d for density, and we can equal M over V, mass divided by volume. Okay, let's see how we can modify the ideal gas equation to incorporate density. Okay, so the first thing we notice is that some variables that were in the original ideal gas equation have been removed, and that some variables that were not in the original ideal gas equation have been added. There is also a slight change in one of the units. We'll go through how we got from the ideal gas equation to the modified version of the ideal gas equation with density as the subject in a bit. But first, let's just go through this modified version of the ideal gas equation with density as the subject with each unit combination. So, with unit combination 1, we have density represented by a capital D with the unit of grams per cubic meter equals pressure in kilopascals multiplied by the molar mass in grams per mole divided by the ideal gas constant in joules per mole per Kelvin multiplied by temperature in Kelvin. Quick reminder, molar mass is the mass of 1 mole of a substance, and we'll go through why this variable has been added to the equation in a bit. But first, I'll quickly explain why we now have kilopascals as the unit for pressure within this modified version of the equation rather than pascals, which was used in the original ideal gas equation. Basically, it's because if we used pascals, the numerical value for pressure would be very large, and as a result, we would have a value for density that would be too large to realistically represent the density of a gas. We'll go through a question in a bit where we'll use kilopascals first, and then we'll use pascals, after which we can compare our answers for density and realize why we need to use kilopascals in this version of the equation. Let's now go through the same equation, but this time with the second unit combination. We have density, once again represented by a capital D. Some course specifications do have a preference regarding which symbol should be used to represent density, so it's best to check whether you need to use the Greek letter rho or whether you can use either a capital or lowercase d. In this video, we're going to use a capital D. So for the second unit combination, we have density in grams per litre equals pressure in atmospheres multiplied by molar mass in grams per mole divided by the ideal gas constant with the units of atmospheres and litres in the numerator of the fraction and moles and Kelvin in the denominator of the fraction, and we multiply by the temperature in Kelvin. Please note that despite volume not being in this modified version of the ideal gas equation directly, we still include litres in the units for the ideal gas constant. Okay, before we apply this equation to a question, let's go through how we went from the original ideal gas equation to this modified version with density as the subject. Okay, let's now run through how to use algebra to convert from the original ideal gas equation to the modified version with density as the subject. I've written out the original ideal gas equation in red at the top of the slide, and at the bottom in blue we have the modified version of the equation with density as the subject, and in the middle we have 6 intermediate equations within the process of converting from the original ideal gas equation to the modified version with density as the subject. The first thing we need to do is address the variable amount. When we examine density, we are trying to work out the mass of a gas in a certain volume of space. Quick reminder, when we talk about amount, we are talking about the number of particles contained within a sample substance, whereas when we talk about mass, we are talking about how much matter is made up of those particles in a sample. We can think of it as an indicator of how heavy a sample of a given substance is. However, if you are asked to define mass in this context, you need to refer to it as an indicator of how much matter is made up of particles of a certain substance. So, for modifying the ideal gas equation for density, we need to take out the lowercase n for amount in moles. Now, although the variable of amount in this form is removed, the unit of moles is not. This is because the variable that is inserted into the equation instead is molar mass, which is the mass of 1 mole of a substance. So, that is the quantity of matter in grams that is made up of 1 mole of a substance. And 1 mole of a substance, just another quick reminder, consists of 6.02 times 10 to the 23rd particles of that substance. So, what we can do first, as shown in equation 1, is replace the letter N for amount on the right-hand side of the equation with the fraction we use for calculating the amount in moles, which is lowercase m for mass divided by capital M for molar mass. For clarity, we have inserted the fraction in brackets, and we have R and T outside the brackets in the numerator on that side of the equation next to it. Okay, so staying with equation 1, we're going to address the molar mass variable next. Others may wish to address the volume variable before molar mass. However, I think it's a clearer process if we get the molar mass onto the same side of the equation as pressure first. So, to do that, we have to cancel out molar mass on the right-hand side of the equation and move it over to the left-hand side of the equation where pressure is. A quick reminder about how we cancel out using algebra. You need to carry out the opposite arithmetic operation to what was originally performed in the equation. So in this version of the equation, we divide by molar mass. So to cancel it out, we must multiply by the molar mass as indicated by inserting a capital M into the numerator in equation 1. We can then cancel out m in the numerator and the denominator. However, the second important step we then must carry out is that we must carry out the same arithmetic operation on the opposite side of the equation. So we multiplied the right-hand side of equation 1 by the molar mass. Therefore, we must do the same on the left-hand side of the equation. The result is the arrangement of variables we have in equation 2, which is pressure multiplied by volume and molar mass equals mass multiplied by the ideal gas constant and temperature. Okay, what about volume and how do we insert density into the equation? Well, as we looked at previously, to calculate density, we must divide the mass of a substance, in this case the mass of a gas, by the volume it occupies in the system, such as a cylinder. We therefore need to have an equation where mass is divided by volume, which means volume needs to be on the same side of the equation as mass. So, in equation 3, we cancel out volume on the left-hand side of the equation by dividing this side by the volume, by inserting it into the denominator. And then we then insert the volume as the denominator on the right-hand side, which means we now have mass within the numerator being divided by volume in the denominator. We now have the arrangement in equation 4, where pressure multiplied by the molar mass equals mass multiplied by the ideal gas constant and temperature divided by volume. We can now do something quite neat. We can substitute the mass, lowercase m, divided by the volume, capital V, for capital D to represent the density, because density is equal to mass divided by volume. So in equation 5, we now have pressure, capital P, multiplied by the molar mass, capital M, equals density, capital D, multiplied by the ideal gas constant, capital R, multiplied by temperature, capital T. We now have an equation with the correct variables, represented by the correct letters, for the modified version of the ideal gas equation that includes density. All we must do now is make density the subject. So, what we can do first is swap the sides of the equation around. So density is on the left-hand side of the equation, as usually we like to have the variable of interest or subject on the left-hand side of the equation. So, in equation 6, we cancel R and T on the left-hand side of the equation, and because we previously multiplied by R and T, to cancel them out, we divide by R and T on the left-hand side of the equation. We then divide the right-hand side of the equation by R and T. So that leads us to the equation in blue, where density is on its own as the subject on the left-hand side of the equation, and it equals pressure multiplied by the molar mass divided by the ideal gas constant multiplied by the temperature. Let's now use the modified version of the equation to answer some questions on density. Okay, let's now go through a question involving the first unit combination, and we'll carry out the calculation first with kilopascals as the unit for pressure, and then we'll do it again but with pascals as the unit for pressure, and we'll compare our answers for density and see which one is the sensible answer. Okay, the question asks, what is the density in grams per cubic meter of oxygen at a temperature of 23.0 degrees Celsius and a pressure of 130 kilopascals. Now, something that we need to realize first is that we have been given information relating to two variables. In the previous video, when we used the original ideal gas equation, we were given information on three variables, and with the ideal gas constant, we were able to work out a fourth variable. However, this sort of question tends to give us information on two variables. Why? Because we are usually expected to calculate the molar mass of a gaseous substance ourselves rather than being given the value in the question. It's a nice way of testing our depth of knowledge regarding the application of this equation and usually allows us to achieve an extra mark. So what we'll do first is calculate the molar mass of oxygen. Now, quick reminder, to calculate the molar mass of a substance, we need to find the sum of the relative atomic masses of the constituent atoms. In this case, we need to find the relative atomic mass of oxygen, which three significant figures is 16.0, and then we need to multiply it by 2 because oxygen exists as a diatomic molecule, meaning we have 2 atoms of oxygen per molecule. Therefore, for the molar mass of oxygen, we have 16.0, the relative atomic mass, times 2, and we are given an answer of 32.0 grams per mole as the molar mass of oxygen. Okay, next we need to go through the question again and pick out information regarding other variables, and if necessary, convert the values to allow them to be expressed with the correct units for the unit combination. We are given a temperature for the system of 23.0 degrees Celsius. We don't want Celsius, we want Kelvin, so we need to convert this value into Kelvin by adding to it the value of 273.15 Kelvin, which is equivalent to 0 degrees Celsius, and what we need to add to our given value in Celsius to convert it to Kelvin. So, for temperature, we take 23.0 degrees Celsius and add to it 273.15 Kelvin, and we get an answer for the temperature of the system of 296.15 Kelvin. Okay, the other variable we are given in the question is pressure at a value of 130 kilopascals, which is fine for this version of our answer to this question, but in a bit we'll convert this to pascals to allow us to compare the two answers. But for now, we'll just leave it at 130 kilopascals. We now have values representing three variables. Let's now write our ideal gas constant of 8.31 joules per mole per Kelvin, which, by the way, does not change no matter whether we use kilopascals for pressure or pascals for pressure. Let's now plug our values into the equation. So, for density, we take the value for pressure of 130 kilopascals, multiply by the molar mass of 32.0 grams per mole of oxygen, and we divide by our ideal gas constant of 8.31 joules per mole per Kelvin, multiplied by our temperature, the temperature of the system of 296.15 Kelvin, and we get an answer to three significant figures of 1.69 grams per cubic meter for our density for oxygen under these conditions. Okay, let's now carry out the process again, only this time with pressure in pascals. So there we go. Okay, so firstly we need to convert our value for pressure from kilopascals into pascals. So let's do this. Okay, so pressure, we are given a value of 130 kilopascals, and to convert that to pascals we need to multiply by 1000, and we get an answer of 130,000 pascals, a very large number. Okay, let's now carry out the calculation again, but this time with this value for pressure. So density is equal to 130,000 pascals for pressure, multiplied by the molar mass of 32.0 grams per mole of oxygen divided by the ideal gas constant of 8.31 joules per mole per Kelvin multiplied by the temperature of the system of 296.15 Kelvin. And we get an answer of 1,690 grams per cubic meter. Now the difference between this answer and our previous answer is vast. Just a quick reminder, our previous answer with kilopascals for pressure was 1.69 grams per cubic meter for the density of oxygen under these conditions. 1,690 grams per cubic meter is not really a realistic answer for the density of a gas. Therefore, in this scenario, we would use 1.69 grams per cubic meter as our answer for the density of oxygen under these conditions, and therefore demonstrates why we need to use kilopascals as the unit for pressure when we use this modified version of the ideal gas equation for working out density with that unit combination. Okay, let's do another question now, but this time with the second unit combination, which thankfully is relatively more straightforward than the previous unit combination. What is the density in grams per litre of carbon dioxide gas at 1.60 atmospheres and 32.0 degrees Celsius? Okay, so firstly, let's work out our molar mass again. Now, we are working with carbon dioxide this time. So, carbon dioxide consists of one carbon atom and two oxygen atoms. So, the molar mass is the relative atomic mass of one carbon atom, which is 12.0, plus the relative atomic mass of oxygen times 2. So that is 2 times 16.0. And that leads to an answer of 44.0 grams per mole for the molar mass of carbon dioxide. Okay, next we go through the question to see what variables we have been given and the values, and see if we need to convert any to allow us to have the units we need for this unit combination. So we've been given our pressure in atmospheres, which is what we want. So we have 1.60 atmospheres for pressure. For temperature, we've been given 32.0 degrees Celsius. We don't want Celsius, we want Kelvin. So we add to that value 273.15 Kelvin to get an answer of 305.15 Kelvin for the temperature in the system. Okay, let's now write down our ideal gas constant, which for this unit combination is 0.0821, with atmospheres, litres, and moles and Kelvin within this fraction to represent the units. Okay. Let's now calculate the density by doing 1.60 atmospheres multiplied by our molar mass for carbon dioxide of 44.0 grams per mole, the three significant figures, divided by our ideal gas constant of 0.0821 atmospheres, litres over moles per Kelvin, times the temperature of 305.15 Kelvin. Now, quick reminder, this is the unit combination we tend to use if we need to cancel out units we don't want for our final answer. So, at the top we have atmospheres, at the bottom we have atmospheres, we can cancel that out. At the top we have moles, at the bottom we have moles. Now, the fraction that contains the units within the ideal gas constant, we tend to consider the denominator of that as a separate denominator to the main denominator within the main fraction. So we can actually cancel out Kelvin, because Kelvin is considered as on top of this Kelvin here is considered on top of this Kelvin here. So we can cancel it out. So as a result, we have grams and litres left, which is the units we need for our final answer. So put that into a calculator. 1.60 times 44.0 divided by 0.0821 times 305.15, and we get an answer to three significant figures for the density of carbon dioxide under these conditions of 2, 0.81 grams per litre. Okay, so now we know how to use the density version of the ideal gas equation to calculate density. However, you may get a question in the test or exam that requires you to use a rearranged version of the same equation, but instead of working out the density of a known gas, you're required to work out the molar mass of an unknown gas. A typical example is the following. A gas has a density of 2.05 grams per litre at STP. What is its molar mass? So, firstly, let's get the equation we need for this question. Here we have our modified version of the ideal gas equation with density as the subject in red, and next to it in green we have our rearranged version of the equation with molar mass as the subject. And we can see that if we want to determine molar mass, we multiply density by the ideal gas constant and temperature, and then divide by the pressure. Okay. So we are given the value for density, which is useful, 2.05 grams per litre. However, we are not directly given the values for any other variables we need to calculate the mole mass. Instead, we are told that the system in which this gas is present is at standard temperature and pressure. This is a typical way of a single question bringing together different parts of a topic, in this case gas stoichiometry, to test our overall knowledge on the topic. We have to remember that we need to remember what the values are for temperature and pressure and the standard temperature and pressure conditions with the correct units. So on this slide, we are using unit combination 2 because once again, this is a relatively more straightforward combination to use, as unit combination 1 also has issues when it comes to calculating molar mass, which we'll go through in a bit. So for this unit combination, the units of pressure are atmospheres and the unit for temperature is always Kelvin. At STP, the value for pressure is 1 atmosphere, 1.00 atmospheres. And temperature is typically quoted as 0 degrees Celsius. However, we want that in Kelvin, which is 273.15 Kelvin. Our ideal gas constant for unit combination 2 is still 0.0821 with atmospheres, litres over moles, and Kelvin as the unit. And our given value for density for this unknown gas is 2.05 grams per litre. Okay, let's now plug these values into our equation to work out the molar mass. So for molar mass, here we go. We take our density of 2.05 grams per litre, multiply it by the ideal gas constant of 0.0821 atmospheres, litres over moles and Kelvin, and multiply it by our temperature of 273.15 Kelvin, and we divide by our pressure of 1.00 atmospheres, and we get an answer to three significant figures of 46.0 grams per mole, which is the molar mass to three significant figures of nitrogen dioxide. You may be asked to state which gas you think the unknown gas is based on the calculated molar mass. However, typically you usually just ask to calculate the molar mass with this version of the ideal gas equation, typically under the conditions of STP, and then you calculate the value and then give the value for the molar mass. However, in this version, in this question, we're able to identify that the unknown gas under the conditions of STP in this system is nitrogen dioxide based on the calculated value for the molar mass of 46.0 grams per mole to three significant figures. Okay, so we went through that last example with unit combination 2 quite smoothly. However, if we use unit combination 1, we'll find ourselves in a similar predicament to what we experienced when calculating density with this unit combination. The problem, once again, is with the units for pressure.
At STP, using unit combination 1, pressure in pascals has a value of 101,325, whereas if we use kilopascals, it's 101.325. Our temperature is still 0 degrees Celsius, which is equivalent to 273.15 Kelvin. Our gas constant with this unit combination is 8.31 joules per mole per Kelvin, and we have a density of 2.86 grams per cubic meter for the unknown gas. You can probably guess which one of these pressure values is the best to use for this calculation, but let's go through a calculation involving both individually and see what happens with regards to our answer for molar mass. Okay, so let's write out our calculation again first. So molar mass is equal to the density multiplied by the ideal gas constant multiplied by the temperature divided by the pressure. Okay, let's carry out this calculation first with pascals for our units of pressure. So molar mass is equal to our density of 2.86 grams per cubic meter multiplied by the ideal gas constant of 8.31 joules per mole per Kelvin multiplied by the temperature of 273.15 Kelvin divided by our pressure value in pascals of 101,325 pascals. If we put that into a calculator, we would get an answer to three significant figures of 0.0641 grams per mole. Unfortunately, this answer is not possible because the lowest possible value we could have for molar mass is that of hydrogen, which is equal to 2.02 grams per mole, because the relative atomic mass of hydrogen is 1.01 to three significant figures, and we must multiply it by 2 to account for the fact that it's a diatomic molecule, and therefore it has a molar mass of 2.02 grams per mole. Therefore, if we have a gas in a system and it is not hydrogen, it must have a molar mass above 2.02 grams per mole. Therefore, our calculated value of 0.0641 grams per mole with this version of the calculation in which we use pascals for our units of pressure is not correct. Therefore, we must carry out the calculation again, but this time we're going to use kilopascals for pressure. So let's do the calculation again. So molar mass is equal to our density is still the same at 2.86 grams per cubic meter, multiplied by our ideal gas constant of 8.31 joules per mole per Kelvin, multiplied by our temperature of 273.15 Kelvin, divided by our pressure value in kilopascals of 101.325 kilopascals. If we put that into a calculator, we would get an answer to three significant figures of 64.1 grams per mole, which the three significant figures is the molar mass of sulfur dioxide. So by using kilopascals for our units for pressure, we were able to produce a more sensible answer for the molar mass of this unknown gas, and we were able to match it to the molar mass of sulfur dioxide. Therefore, we can assume that the unknown gas in this system under these conditions is sulfur dioxide. This demonstrates once again, as we did previously when we calculated density using unit combination 1, it is better to use kilopascals for the units for pressure rather than pascals.
Okay, so another variable that could be examined using a modified version of the ideal gas equation is the mass of a sample. We briefly went over what the mass of a sample is when we were discussing how to create a version of the ideal gas equation for density earlier on. But let's quickly go over what mass is again. Mass
is the measurement of how much matter in a sample is made up of particles of a particular substance. It is not the same as amount. Amount is the actual number of particles of a substance present and is expressed either in number of atoms, molecules, formula units, or in moles. For gases, formula units are not usually used to express amount. The mass of a gas is usually expressed in grams, and gases do have mass. It's obviously not as much as you could get with solids or liquids, but gases do have mass. And the ideal gas equation can be modified to allow for the inclusion of mass, and we saw mass as a variable within the equation when we were converting the original ideal gas equation into the density version earlier on. Let's now quickly go through how we can get from the original ideal gas equation to a modified version with mass as the subject. Okay, so at the top of the slide we have the original ideal gas equation. Pressure times volume equals the amount in moles times the ideal gas constant times temperature. Earlier on, when we were creating the version of the ideal gas equation for density as the subject, we discussed how we could substitute a lowercase n for amount in moles for the fraction that we usually use for calculating the amount in moles, which is the mass of the sample, lowercase m, over the molar mass, capital M. So for the first part of this conversion, we can write P times V is equal to lowercase m for the mass of the sample times the R for the R for ideal gas constant times the T for the temperature over capital M for the molar mass. Next, we can swap these two sides of the equation around to allow us to have the lowercase m for the mass of the sample on the left-hand side of the equation, because that's typically where the subject is. So, lowercase m times r times t over capital M is equal to P times V. Next, we want to cancel out r and t. Because we multiply by r and t on the left-hand side of the equation to cancel out, we must divide by r and t. That allows us to cancel it out on the left-hand side of the equation, like so. But then we must also divide by r and t on the right-hand side of the equation. So we are then left with lowercase m for the mass of the sample over molar mass is equal to pressure times volume over ideal gas constant times temperature. Now all we need to do is cancel out the molar mass on the left-hand side of the equation. And to do that, because we divide by the molar mass in this version of the equation to cancel out, we must multiply by the molar mass. So lowercase m times capital M over capital M equals P times V over R and T. We can cancel out the molar mass on the left-hand side of the equation, like so, but we also must multiply by the molar mass on the right-hand side of the equation by putting it in the numerator on the right-hand side of the equation. That then leaves us with the mass of the sample on its own, lowercase m on the left-hand side of the equation, is equal to pressure times the volume times the molar mass divided by the ideal gas constant times temperature. And this is the version of the ideal gas equation that we need for calculating the mass of a sample. Let's look at a question. A sample of hydrogen gas is held within a container with a volume of 30.0 decimeters cubed at a temperature of 27.0 degrees Celsius under a piston at a pressure of 108 kilopascals. What is the mass of the sample in grams? Now, this is a typical question that tends to be put into an exam or test that contains quite a bit of information that is needed for the calculation, but also other information that provides context, but ultimately makes the question seem more complicated than it needs to be. For instance, we are told that the sample of hydrogen gas is under a piston. That encourages us to imagine what the experimental conditions were like, but ultimately when it comes to answering this question, we don't need to worry about what caused the gas to become under pressure. We just need to know what the measured pressure value was. Okay, now we need to look at our information and see whether everything is being expressed in the units we want to plug into the modified version of the ideal gas equation. We're using unit combination 1, and this time we can use pascals for pressure, thank goodness. I'll quickly explain why this is the case when we do the calculation in a bit. But for calculating the mass of a sample of a gas, we can use the same units that we used in the original ideal gas equation when using unit combination 1. So for pressure, that's pascals. For volume, it's cubic meters, and temperature is expressed in Kelvin. The molar mass wasn't in the original ideal gas equation, but that is still expressed in grams per mole, and the ideal gas constant is in joules per mole per Kelvin. A far easier process when using unit combination 1 this time around. Now for the not so good news. We need to convert all the values given in the question because they're expressed using the wrong units for this unit combination, but we can do it. Okay. Pressure is given at a value of 108 kilopascals. We need to convert this value into pascals by multiplying by 1,000 to get an equivalent value of 108,000 pascals. For volume, we are given a value of 30.0 decimeters cubed. We need to convert this into cubic meters by dividing by 1,000 to get an equivalent value of 0.03 cubic meters. Temperature, we're given a value of 27.0 degrees Celsius. We need this value in Kelvin, and to convert this value to Kelvin, we add 273.15 to get an equivalent value of 300.15 Kelvin. Okay, what else do we need? The ideal gas constant for unit combination 1 is 8.31 joules per mole per Kelvin, and we need the molar mass for hydrogen gas, which the three significant figures is 2.02 grams per mole. Okay, let's quickly remind ourselves how the equation is organized. So, to find the mass of the sample of gas present in the system, we take the pressure, multiply it by the volume of the system, multiplied by the molar mass of the gas present, and we divide by the ideal gas constant times the temperature of the system. Okay, let's plug our values into this equation and see what we get for the mass of the sample of hydrogen gas present under the conditions in question. So, our pressure value of 108,000 pascals is multiplied by our volume of 0.03 cubic meters, multiplied by the molar mass of hydrogen gas, which the three significant figures is 2.02 grams per mole, and we divide by our ideal gas constant, 8.31 joules per mole per Kelvin, multiplied by the temperature in the system of 300.15 Kelvin. Now, the reason why we can use pascals for the units of pressure in this calculation is because there's a greater sense of balance now in the numerator of the fraction, and as a result we can have a sensible answer. And the reason why that's the case is because when we converted kilopascals into pascals, we multiplied by 1,000. But then when we converted our volume from decimeters cubed into cubic meters, we divided by 1,000. So as a result, there's now a sense of balance. And as a result, we can use pascals for the units of pressure in this calculation. And if we put these values into a calculator, we would get an answer to three significant figures of representing the mass of the sample of hydrogen gas present in the system under these conditions of 2.62 grams of hydrogen gas.
Okay, let's go through another question involving the calculation of mass. However, this time we're going to use unit combination 2 and go over another set of conditions of pressure and temperature that you'll need to remember in case it comes up in a question like this. A sample of chlorine gas is held within a cylinder at a volume of 5.00 litres at RTP. What is the mass of the sample in grams? Now, RTP stands for room temperature and pressure conditions. We went over standard temperature and pressure conditions earlier on. Now we need to assume room temperature and pressure conditions for this system. This means that we need to assume, using unit combination 2, that our pressure is 1.00 atmospheres. Now, there is some debate over what the exact value for room temperature should be. Some resources will state that 20 degrees Celsius is room temperature, whereas others will state that 25 degrees Celsius is room temperature. In this question, we're going to assume that room temperature is 20.0 degrees Celsius. However, please check the specification for your course for which temperature is assumed to be room temperature. They may give you the value in the exam, in the question in the exam, something along the lines of assume room temperature to be 20 degrees Celsius, for instance, and then you just have to remember that room pressure is 1 atmosphere. However, it's likely that examiners will want to see evidence so you can remember both pressure and temperature values at RTP, in which case it's important you establish which value for room temperature you need well in advance of the test or exam. Okay, so we now have our pressure value and our temperature value according to RTP. However, our given value for temperature is in degrees Celsius. We need it in Kelvin. So we take 20.0 degrees Celsius and add to it 273.15 to get an equivalent value in Kelvin of 293.15 Kelvin. Our given value for volume is 5.00 litres, and litres is the unit we need for this unit combination. Our ideal gas constant is 0.0821 with atmospheres and litres in the numerator and moles and Kelvin in the denominator. And the other value we need is the molar mass. Now for chlorine, the relative atomic mass to 3 significant figures for chlorine is 35.5. However, because it's a diatomic molecule and 2 atoms exist in 1 molecule of chlorine gas, we need to multiply the relative atomic mass by 2 in order to get the molar mass. So 35. So what we do 35.5, the relative atomic mass, 3 significant figures, and we multiply it by 2 to get our molar mass, which is 71.0 grams per mole of chlorine gas. Okay, let's put our values into the equation. So we are working out the mass of the sample of chlorine gas. We take our pressure under RTP of 1.00 atmospheres, multiplied by our given volume of 5.00 litres, multiplied by the molar mass of chlorine gas, which is 71.0 grams per mole of chlorine gas, and we divide by the ideal gas constant, 0.0821 atmospheres, litres over moles, and Kelvin, times the temperature of 293.15 Kelvin. And now we can cancel the units we don't need for our final answer. So we have atmospheres in the main numerator and we have atmospheres in the main denominator. Litres at the top, litres at the bottom, and we have moles at the top and moles at the bottom. For Kelvin, we have Kelvin's in the main denominator of the fraction, but it's also in the denominator of this fraction that's within the ideal gas constant. So as a result, we can have a top and a bottom, so therefore we can cancel out Kelvin. As a result, the only unit we have left is grams, which is the unit we need for our final answer. So we put that into a calculator, we would get an answer to 3 significant figures of 14.8 grams of chlorine gas, which is the mass of the sample of chlorine gas in this system under RTP. Now, in the previous video, we used a trick when it came to the positioning of R in these sort of calculations.
where we moved the position of R to allow ourselves to have more clarity when it came to the cancellation of units, the cancelling of units that we don't need for our final answer. However, while that's fine when it comes to the original ideal gas equation, with these equations that are essentially modifications of the ideal gas equation where variables that weren't originally in it have been included, it's best to leave R where it is according to the rearranged or modified ideal gas equation. So rather than move R, say, one place to the right, it's best just to leave it where it is and just carry out the calculation like so. And just be careful when we have this triple level fraction arrangement that you cancel out the units correctly. Okay, so far in this video and in the previous video, whenever we examined amount, we used the unit of moles. The problem with using the unit of moles is that it doesn't truly represent the sheer number of particles, in this case gaseous atoms or molecules, present in the system. Quick note, we can have ionized gases, which are essentially plasmas. However, when we are discussing the ideal gas law, we're usually talking about a gas that consists of atoms or molecules. So whenever you have a question in relation to the actual number of gaseous particles present in the system, we are usually talking about atoms or molecules. So what is the problem with using the unit of moles? Well, it can be described as being too macroscopic. Basically, the relatively small number of, say, 2.00 moles doesn't truly reflect the vast number of gaseous particles present in the system and the large number of interactions and behaviors that could occur. So firstly, let's quickly remind ourselves how many particles there actually are in 1 mole of substance. To do this, we use Avogadro's constant, also known as Avogadro's number, which states that in 1 mole of any substance there is, to 3 significant figures, 6.02 times 10 to the 23rd particles of that substance. So if we instead consider the actual number of gaseous particles within the system rather than representing them with the unit of moles, we can get a more accurate picture of what is going on. So if we go back to the amount of 2.00 moles, to convert that into the actual number of gaseous atoms or molecules present in the system, we must multiply the amount in moles by Avogadro's number, and we end up with 1.204 times 10 to the 24 particles of that gaseous substance. Now, we have a more accurate value representing the quantity of the gaseous particles present in the system. However, 1.204 times 10 to the 24 is a very large number. And if we inserted that large number into the same side of the equation as the ideal gas constant, we would probably run into an issue when it comes to the supposedly equal relationship between the two sides of the ideal gas equation. It's unlikely to be equal with these two large numbers on the same side of the equation. So we need a constant that consists of a small number to balance out with the large number representing the number of particles that has been inserted into the same side of the equation as the constant. This balancing out on the one side of the equation means that it's more likely that the two sides of the equation will be equal. So what are we going to replace the ideal gas constant with when dealing with the number of atoms or molecules present rather than moles? It's actually another constant called Boltzmann's constant.
Boltzmann's constant is named after the Austrian physicist Ludwig Boltzmann, who is known for his work on the kinetic molecular theory of temperature. We previously went through kinetic theory and how this helps to explain the behavior of gaseous particles in the previous video. So if you want a reminder, please click the link to the video down below. Boltzmann's work explained the distribution of the speeds of gaseous particles and how higher temperatures leads to a broader distribution of particle speed in a specific gas, because the particles, despite being of the same gas, don't all move at the same speed. And at higher temperatures, that distribution, that spread in particle speed becomes even wider. However, in this video, we're going to keep things simple and just summarize by saying that a higher temperature in the system is linked to a higher average level of kinetic energy in the gas particles within the system. Our focus in this video is going to be on Boltzmann's constant, which is represented by a K followed by a capital B in subscript and is calculated by taking the ideal gas constant, R, and dividing it by Avogadro's constant, represented by capital N followed by a capital A in subscript. If both the ideal gas constant
and Avogadro's constant are expressed in three significant figures, the resulting value for Boltzmann's constant in three significant figures will be 1.38 times 10 to the minus 23rd joules per Kelvin. When we use Boltzmann's constant, we usually only use unit combination 1. Let's now quickly go through the calculation within this equation to prove it's correct and show what the modified version of the ideal gas equation looks like with this constant and the variable of number of particles included. Okay, so let's firstly demonstrate how we can calculate Boltzmann's constant. So Boltzmann's constant, K subscript B, can be calculated by taking the ideal gas constant, R, and dividing it by Avogadro's constant, N subscript A. So, the ideal gas constant, the three significant figures using unit combination 1, is 8.31 joules per mole per Kelvin. And if we divide that by Avogadro's constant, three significant figures, 6.02 times 10 to the 23rd per mole, we would get an answer. If we put it into a calculator, we would get an answer 1.380398671 times 10 to the minus 23rd, and that would be joules per Kelvin. But if we round down the three significant figures, we would get an answer of 1.38 times 10 to the minus 23rd joules per Kelvin, which is the value of Boltzmann's constant. Okay, let's now see how the ideal gas equation will look once we've included Boltzmann's constant instead of the ideal gas constant and the variable of number of particles rather than the variable of amount in moles. So the left-hand side of the equation is exactly the same. It's pressure times the volume. However, on the right-hand side of the equation, instead of a lowercase n for amount in moles, we now got a capital N for the number of particles, followed by either a K on its own or a K with a subscript B to represent Boltzmann's constant, and then we've got T for temperature. So this modified version of the ideal gas equation now states that theoretically, if we have a value from pressure times volume, that value will be equal to the value we get from taking the number of particles, multiplying it by Boltzmann's constant, and then multiplying it by the temperature. Okay, let's now use a rearranged version of this modified version of the ideal gas equation to answer a question in which we're required to calculate the number of particles of a gas present in the system. Okay, let's look at the question. How many molecules of nitrogen gas are present in a container with a volume of 33.0 decimeters cubed, a pressure 111 kilopascals, and a temperature 34.0 degrees Celsius? The equation we need to answer this question states that in order to calculate the number of particles, we take the pressure, P, multiply by the volume, V, and divide by Boltzmann's constant, Kb, times the temperature, T. The next thing we need to do is go through this question again and make sure we have the correct values or the correct units we need to plug into the equation. So we are given a pressure value of 111 kilopascals. We can convert that into pascals by multiplying by 1000 to get an equivalent value of 111,000 pascals. Our volume value given is 33.0 decimeters cubed. We want to convert that into cubic meters by dividing by 1000 to get an equivalent value of 0.033 cubic meters. For temperature, we're given a value of 34.0 degrees Celsius. We want to convert that into Kelvin by adding 273.15 to get an equivalent value of 307.15 Kelvin. And we're using Boltzmann's constant at a value of 1.38 times 10 to the minus 23rd joules per Kelvin. Okay, let's now plug our values into our equation. So to calculate
N, which in this case is the number of molecules of nitrogen gas present in the system, we take the pressure of 111,000 pascals, multiply by the volume of 0.033 cubic meters, and we divide that by Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin, multiplied by the temperature of 307.15 Kelvin, and we get an answer to three significant figures of 8.64 times 10 to the 23rd molecules of nitrogen gas. Okay, so throughout this video and the previous video, we have mentioned issues regarding the ideal gas law and how it doesn't always truly reflect how real gases behave, and that there are issues within certain versions of the ideal gas equation when it comes to certain calculations. However, we are now going to delve into the main problems with the ideal gas law and situations where it is simply not applicable. There are two main examples of this. The first is when pressure is exceptionally high. This is usually due to the volume of the system being very small. As a result of this, the movement of gaseous particles is very restricted, as there is less space for particles to occupy, meaning collisions between particles and surfaces are more likely to occur frequently. This could also cause a change in state, so conversion to a liquid or solid, due to the proximity of the particles allowing intermolecular forces of attraction to draw them together. The second situation is when temperature is exceptionally low, and as a result there is a very low level of average kinetic energy in gaseous particles within the system. This means they are going to be moving very slowly, and as a result they are more likely to be drawn together by intermolecular forces. So why are the two previous situations so problematic? Well, they essentially prove that some of the assumptions within the ideal gas law are wrong. The first assumption they prove wrong is that there is no or negligible forces of attraction or repulsion between particles. The reality is that we have intermolecular forces, van der Waals forces. Oppositely partially charged regions of adjacent molecules become attracted to each other, whereas similarly partially charged regions of adjacent molecules repel each other. This is more likely to occur if they are close together under high pressure within a system that has a very small volume, and when the gaseous particles lack the average kinetic energy needed to keep apart from one another due to an exceptionally low temperature. The second assumption the two previous situations prove wrong is that particles have a negligible volume relative to the total volume of a system, such as a container. The ideal gas law only accounts for the volume of the container or vessel which the gas can occupy, whereas in reality, gaseous particles do have a notable volume themselves, and this volume is actually more significant when the volume of the system is very small and pressure is exceptionally high. For example, a container could have a volume of just 1 cubic meter, which would be the value included in the ideal gas equation. However, we don't know how much volume is occupied by the gas particles themselves. The ideal gas law doesn't recognize the actual size of the particles. It only wants us to consider the volume of the container, the cylinder, or the box that we can see acting as the system. But we should really consider the actual size, the actual volume of the particles themselves, especially when the volume of the system is very small and pressure is exceptionally high. So, what should we do about these situations? How do we deal with a real gas that is too real for the ideal gas equation? We need to modify the ideal gas equation again, but this time to account for intermolecular attraction or repulsion between gaseous particles and the volume of the particles themselves. We end up with an equation called the van der Waals equation. We've already referred to the Austrian physicist van der Waals when referring to the intermolecular forces that can exist between gaseous particles, collectively known as van der Waals forces. However, we are now going to use an equation he derived that is a modified version of the ideal gas equation that considers the possibility of intermolecular attraction or repulsion and the actual volume of the gaseous particles themselves. Within the van der Waals equation, we have two established constants, also known as correction factors. that account for the strength of intermolecular attraction or repulsion between gaseous particles and the volume occupied by the gas particles themselves. The values of the established constants are specific for each gas. They are termed A and B. A is the established value for the strength of intermolecular attraction or repulsion between gaseous particles of a particular gas, whereas B is the established value for the volume of the gas particles of a particular gas. Now, when we use the term constant in this context, we mean that the value is the same when a specific gas is involved, no matter what happens to variables such as pressure or temperature in the system. It does not mean the same as the ideal gas constant, which, depending on which units you use, remains the same no matter which gas is involved. For instance, the established constants values A and B for carbon dioxide would be different to the established constants for ammonia gas, for example. However, if carbon dioxide molecules were in a system and the temperature was changed from 350 Kelvin to 400 Kelvin or to 450 Kelvin, the established constants for the strength of intermolecular attraction or repulsion, value A, and the volume of the particles themselves, value B, would be the same for those carbon dioxide molecules, no matter what temperature is in the system. It is highly likely that you will be given the values for established constants A and B for the gas being examined within a question in the test or an exam. These values are typically summarized in tables, and you will probably be given the values directly for the specific gas in the question, or you'll be given a table with various gases listed with their established constants, and you will have to select the correct values. And this is an illustration of van der Waals. His work has become a crucial component of chemistry, physics and biology courses at various academic levels across the world. Let's now delve into his equation and see how he sought to address the apparent shortcomings of the ideal gas law and the ideal gas equation. Okay, at first glance, this can look a bit complicated, but let's just break it down and see what we recognize from our previous work. There are components within the van der Waals equation that were in the original ideal gas equation. We still have pressure, P, and the volume of the system, V, on the left-hand side of the equation. And the right-hand side is the same as the original ideal gas equation. We have the amount of the gas in moles, N, multiplied by the ideal gas constant, R, multiplied by the temperature, T. However, on the left-hand side of the equation, we now also have those established constants, which are also known as correction factors, because they correct the issues in the original ideal gas equation when it's applied to real gases. So, quick reminder, A is the established value for the strength of intermolecular attraction or repulsion, and established constant B is the established value for the volume of the gas particles. Now, for an ideal gas, the values for A and B should be 0 because there shouldn't be any intermolecular attraction or repulsion, or if there is, it should be negligible. So close to 0 it's not worth considering. And the volume of the particles should also be 0. However, this is often not the case for real gases. I think the closest gas we have to an ideal gas is helium, because it's a noble gas, meaning it's inert, very stable, and as a result, intermolecular attraction or repulsion is not going to be a big problem. And the size of the atoms are very small, because there's only 2 electrons in one energy level, and only 2 protons and 2 neutrons in its nucleus, meaning the volume occupied by the atoms is going to be very, very small. However, we can't say it abides by the ideal gas law perfectly. No gas abides by the ideal gas law perfectly. That is why this van der Waals equation can be very handy when trying to get a more accurate picture about what is actually going on with a real gas. So on the left-hand side of the equation, we have 2 sets of brackets which are multiplied by each other. In the first set of brackets, we have pressure plus a fraction containing the established constant A multiplied by the amount in moles squared. Now, I've written at the bottom of this slide a brief but very important message. Please don't square A. What I mean is that we don't square established constant A when we multiply by the amount in moles on this side of the equation. We only square the amount in moles. So you can have a situation where, or an arrangement rather, where you have P plus N squared times A over V squared. Or you can have an arrangement where you have P plus A, and then in separate braces you have N over V, and then on the outside of the braces you have squared, and then you close the brackets. For some people, this can be a bit more clearer in terms of the actual process that we go through. However, I was previously advised when I first saw this equation to use the arrangement that is currently on the slide, because it's the arrangement that's most likely to be used when carrying out the question in a test or exam. But please remember, when using this arrangement of the equation, that you don't square A. It remains as the original value before then being multiplied by the amount in moles, and it's the amount in moles which is squared. So after doing that fiddly step, you then divide by the volume of the system squared and add the resulting value to the value for pressure. This result from the first pair of brackets accounts for the possibility of intermolecular attraction or repulsion occurring between particles of the gas in the system. You then take the result from that first pair of brackets and then you multiply it by the result from the second pair of brackets, which is calculated by taking the volume of the system and subtracting established constant B, which represents the value for the volume of the gas particles. This then allows us to account for the actual volume occupied by the gas particles in the system. So you take the result from the first pair of brackets and multiply it by the result from the second pair of brackets. And according to the equation, you should have a value that is equal to the result from multiplying the amount in moles by the ideal gas constant and the temperature in the system. I know it seems very long-winded and that there are various points where mistakes can happen. But the best way to understand and master this equation is to practice using it on questions just like the ones we answered with the ideal gas equation. So we'll go through a typical question in a bit, but first we need to quickly go through what units we need for this equation. Okay, so typically when using the van der Waals equation, unit combination 2 is the most common choice. I have seen one or two examples where a sort of hybrid of unit combination 1 and unit combination 2 is used, where the ideal gas constant from unit combination 1 is used, but everything else is expressed using units from unit combination 2. I personally don't like that approach. It's not that common. Most questions require the consistent use of the same unit combination from start to end, and I'm going to keep things nice and consistent in this part of the video and just use unit combination 2. If you are encouraged or required to use a hybrid of the two unit combinations, the method we're going to go through is exactly the same. You're just going to have to be careful to put in the correct units and correctly converted values into the correct positions in the equation. But as I said, the possibility that you have to use a mixture of units from the two unit combinations is very unlikely. You're more likely to be required to use just one unit combination, and we're going to use unit combination 2 in this video because they are the units most commonly used for the established constants in the van der Waals equation. So let's quickly remind ourselves which units we use in unit combination 2. Pressure is expressed in atmospheres, volume is expressed in litres, amount is expressed in moles, and temperature is expressed in Kelvin. Now the units for the ideal gas constant are atmospheres, litres, moles, and Kelvin. And previously we wrote those units out within a fraction where atmospheres and litres are in the numerator and moles and Kelvin are in the denominator. However, when using the van der Waals equation, for simplicity, we can write the units out on one line. So we can have atmospheres, litres, per mole, per Kelvin. The units for established constant A are atmospheres, litres squared, per mole squared, whereas the units for established constant B are litres per mole. Okay, let's now run through a question that requires the use of the van der Waals equation. Okay, so here's our question. According to the van der Waals equation and the ideal gas equation, what is the pressure of 2.75 moles of water vapor in a system with a volume of 1.00 litres and a temperature of 400.0 Kelvin? Compare the two resulting values and note the difference. This is usually the sort of question you will be given where the van der Waals equation is required, but you must also use the ideal gas equation. We essentially must carry out two calculations, one with the ideal gas equation and the other with the van der Waals equation, and then we compare those answers by finding the difference between them. This is usually designed to show how the van der Waals equation provides a more accurate result because it considers the influence of intermolecular attraction or repulsion and the volume of the gas particles themselves. The variable that is usually involved in this comparison is pressure and, spoiler alert, typically the result for pressure from the van der Waals equation is usually lower than the calculated value for pressure from the ideal gas equation. But let's go through this question and see if that is indeed the case. Firstly, like all the other questions in this video, we need to go through the given values in the question and make sure they are expressed with the units we need for, in this case, both equations. Luckily, in this question, all the given values have the required units. We have amount in moles, volume in litres, and temperature in Kelvin. It's more likely that with a question like this, where there is already quite a few tricky steps, whoever has written the exam or test will probably already provide the values with the correct units, meaning you don't have to do any conversions. However, this may not be the case. And as we've done throughout this video and the previous one, it's very important to read the question carefully and ensure that if any unit conversions are required, they are done before we do anything else. Okay, we also need the value for the ideal gas constant, which the three significant figures with unit combination 2 is 0.0821 atmospheres litres per mole per Kelvin. We also need the established constant A and the established constant B for water vapour. Just a quick reminder, these values are usually either directly quoted in the question or they are within a table of values that are also included will also include the established constants for other gases, which is provided to you for the test or exam. So the value for established constant A, the value that signifies the intermolecular attraction or repulsion between water molecules, the three significant figures with units from unit combination 2 is 5.46 atmospheres litres squared per mole squared. The value for established constant B, which signifies the volume of the water molecules themselves, is the three significant figures 0.0305 litres per mole. The next thing we need to do is rearrange our equations to make pressure the subject. Now, we have seen the rearranged version of the ideal gas equation where pressure is the subject before. Pressure equals the amount in moles multiplied by the ideal gas constant and multiplied by the temperature divided by the volume of the system. The van der Waals equation still looks fiddly. Pressure equals the amount in moles multiplied by the ideal gas constant multiplied by temperature divided by the volume of the system minus the amount in moles multiplied by established constant B. We then subtract the value from the following part of the equation, which results from multiplying established constant A by the amount in moles squared. Remember, we don't square A, and divide that by the volume of the system squared. Okay, let's go to a new slide to do the calculations because the one involving the van der Waals equation can be a bit long, but we'll go through it step by step and make sure we don't make any little mistakes along the way. Okay, let's carry out the calculation with the ideal gas equation first. So, ideal. To calculate the pressure, we take the amount in moles, 2.75 moles of water vapour, multiply it by the ideal gas constant, which the three significant figures with unit combination 2 is 0.0821 atmospheres litres per mole per Kelvin, multiplied by the temperature, which is 400.0 Kelvin, and we divide by the volume of the system, which is 1.00 litres, Now, if we put that into a calculator, we would get an answer, three significant figures of 90.3 atmospheres to represent the pressure of water vapour under these conditions within the system according to the ideal gas equation. Let's now carry out the calculation with the van der Waals equation and see if there's a notable difference in the answers. So, with the van der Waals equation, to calculate the pressure, we take the amount in moles, 2.75 moles of water vapour, multiply it by the ideal gas constant, 0.0821 atmospheres litres per mole per Kelvin, multiplied by the temperature of 400.0 Kelvin, and we divide by the volume of the system, 1.00 litres, minus the amount in moles, 2.75 moles of water vapour, multiplied by established constant B, which represents the volume of the water molecules themselves, which the three significant figures is 0.0305 litres per mole. And then we subtract established constant A, which represents the strength of intermolecular attraction or repulsion between water molecules, which the three significant figures is 5.46 atmospheres litres squared per mole squared. Or we multiply that by the amount in moles, but this time we square the value for the amount in moles. So it'll be 2.75 squared moles of water vapour. Quick reminder, we do not square the value for established constant A. We then divide by the volume of the system, but we square the volume of the system this time. So it'll be 1.00 squared litres. Now if we put that into a calculator, we get an answer to three significant figures of 57.3 atmospheres to represent the pressure of water vapour under these conditions within the system according to the van der Waals equation. And as we predicted, this value is lower than the value we calculated using the ideal gas equation. But let's now work out the difference between the two values to see if the difference is indeed quite substantial. So we take the value we calculated using the ideal gas equation, which was 90.3 atmospheres, and we subtract from that the value we just calculated using the van der Waals equation, which was 57.3 atmospheres, and we would get an answer of 33.0 atmospheres, which is quite a substantial difference. And because the value we get from the van der Waals equation comes as a result of including the influence of possible intermolecular attraction or repulsion between water molecules and the volume of the water molecules themselves, we should be inclined to believe that the lower value we get from the van der Waals equation, 57.3 atmospheres, is a more reliable value to represent the actual pressure of water vapour under these conditions within the system. Okay, let's now quickly summarise what has been quite a journey through the possible modifications and issues within the ideal gas law. We modified the ideal gas equation to calculate variables not included in the original ideal gas equation. This included density, molar mass, and the actual number of gas particles present. When we calculated the actual number of particles present, we had to swap the ideal gas constant for the much smaller Boltzmann's constant to allow for balance within the equation. We also discussed the scenarios where the ideal gas law and original ideal gas equation are not applicable. This is when pressure is exceptionally high and temperature is exceptionally low, which led to certain assumptions made within the original ideal gas law being proven wrong. We then discussed the van der Waals equation as a possible solution for dealing with gases that are too real for the ideal gas law, because it accounts for possible intermolecular attraction or repulsion and the volume of the gas particles themselves.
We then carried out calculations involving the ideal gas equation and the van der Waals equation before comparing our answers, before explaining why the answer from the van der Waals equation provides a more accurate representation of variables such as pressure. That brings us to the end of this video. Thank you so much for watching. If you have any questions or suggestions regarding this video or for possible topics in future videos, please leave them down below. Please also give this video a like if you found it helpful, and please don't forget to subscribe. Thank you all once again for watching, and until next time, goodbye.